Welcome to the workshop, How to Teach Science and Engineering to the Students. This course is designed for science and engineering teachers, professors, instructors, lecturers. My name is Sinha, Dr. Ranbir Sinha, from the company Sinha Research. Objectives and structure of the workshop or short course. In this first course, we are going to talk about general methods, how to teach science and engineering. You may ask, why am I teaching you how to teach science and engineering? Many survey results show that about 80% of the science and engineering students do not understand what's being taught. They cannot apply what they learn in solving problems. So I decided to train the teachers first. The main objective of teaching science and engineering is to produce creative problem solvers for the society. Okay? Students should become problem solvers. That's the main objective of teaching science and engineering. The objective of this course is to make you a great teacher of science and engineering. Do you know of any great teacher of science and engineering? One of them, one of the greatest ones, is this gentleman, Dr. Richard Feynman. Feynman, okay? Structure of this course: general introduction, that's what you'll get today. It's warm up for you. Instructions on best teaching practices. Sample class lecture, that's what you'll get, so that you understand how I teach, why my students like me, why they become successful engineers and scientists. You follow some of those techniques in your lecture. Then you have to prepare on your favorite topic, whatever you teach, whatever you like to teach, a short video and give it to us. We will evaluate, point out where you can improve, and you improve on those points, you become a great teacher. But of course, it comes from practice. Evaluation of my course, your evaluation also, question answers. If you have any questions, I'll try to answer them. Feedback, I'll take your feedback, how this course or workshop is or was. Okay? Good, let's get started. First thing, you have to evaluate yourself. How good of a teacher you are, you have to evaluate. Let's go through a few questions so you understand. Criteria is going to be, do your students understand what you teach? Survey shows most of them don't understand. They get bored. They lose interest. They understand something, but not what you are trying to teach them. Can they apply the knowledge to solve real problems? Science is about reality, you know that. Real problems. Can they solve it after you teach them? Can they use what they learn to solve real problems? You have to answer those things. Do they become employable after graduation? It's a big problem. Many students, they somehow get a certificate, they pass all the exams, but they are unemployable. That's what the industries say. All the major surveys show the majority of the graduates are not employable, especially in certain countries like India. Okay, so you think about these, how good you are, and answer the following. What percentage of your students become employable because of your teaching? Is it more than 75%? How many of you can say that 75% or more of your students become employable? That is, they can do these two things and they become employable. How many? Please raise your hands. Okay. How many of you think between 50 or 74% of your students become employable? Raise your hands. Okay. How many of you think only 25 to 49% of your students become employable? Okay. Fairly large number. How many of you think less than 25% of your students are employable? Majority. Well, those who belong to this category, you create a large number of employable graduates. You are very good. You should be teaching at top institutes, but I'm happy that you teach an average institute because that's where you can make a big difference. 50 to 74%, you should be able to improve to this category. The third one, you need serious improvement. You should take my course very seriously. I can teach you how to teach so that most of your students, more than 75% of your students, become employable. They understand what you teach, they can apply what they learn to solve real problems, science and engineering problems, and they will become employable. This category, I'm trying to say something positive about you. Firstly, you are honest because all the surveys show that less than 20% or less than 25% of the students are employable after graduation. Secondly, you have huge potential. Huge potential. You can make a big difference by changing about 50% of your students or 75% of your students become employable. Can you imagine if that much of potential is used, what kind of society you're going to create? You're creating future, you know that. Imagine if you could help 80% of your students to become good engineers and scientists. Won't that be great? We're going to learn how to do that. Okay? I'm going a little bit fast. You may have to go through this video twice, but what you learn from here, probably you have not been trained before. Warm up. A sense of proportion is essential for scientists and engineers. We get so busy with formulas that we forget that all these things are real. We are solving real problems, okay? So what's the shape of the Earth? We live on the planet Earth, we should know, right? Is it similar to a spherical ball or egg-shaped? Oval. How many of you think it looks like this? The first one. Okay, raise your hand. Yeah, good. Now put your hands down. How many of you think the Earth looks like this? Raise your hands. So about half. So it depends on what you have learned, what you have seen in the books. Many books have wrong pictures, right? Let's verify it. Scientists and engineers do not just memorize things just because somebody has written something or said something. You have to verify. Let's calculate. So let's calculate the percentage of deviation of the shape of the Earth from a perfect sphere. The polar diameter, polar is, suppose that's North Pole, that's South Pole, that diameter is 12,713 about. That many kilometers. Equatorial diameter is 12,756 kilometers. So what is the percentage deviation from, say, an average sphere? Let's take the average of these two numbers. Let's say that's the average diameter. From there, how much does this vary? How much does this vary? They are going to be equal and opposite. Calculate that. Now, yes. So there is a difference about 43 kilometers divided by average of this multiplied by 100. Okay? That's the deviation from a perfect sphere. So percentage variation of average diameter turns out to be less than about 0.3%. 0.3%. Not even 1%. Not even half a percent. It's very close to a sphere. So, how many of you think it looks like this, looking from the space? How many of you think it looks like this? So please do not mislead the students by saying Earth looks like this. Okay? It's very simple. If you didn't know that, it's not your fault. But learn, verify, calculate, verify, look up the references. Okay? It looks almost like this. Very small difference in the diameter here and there. 0.3%. That with naked eye you cannot tell at all. You need specific, specially designed experiment to find that. And that difference is important only in certain cases. For a majority of the problems that we solve, it can be considered to be a perfect sphere. Okay, now the second one. Draw the atmosphere around the Earth. How many of you think the atmosphere looks like this? Just a line. Raise your hands. How many of you think atmosphere looks like this? Remember, sense of proportion. I can give you tons of examples where graduates, professors, practicing engineers don't have sense of proportion. They put in some number comes out, and things go wrong. Okay? In science and engineering, that's not allowed. How many of you think like this? The same kind of formula you can use. The atmosphere is about 100 kilometers thick. Okay? Only 10 kilometers has breathable oxygen. Okay, I'm telling you approximate value to get the sense of proportion right. So if you calculate, it turns out to be that thin layer around the Earth. It's not like this. Okay? All right. When we want to show the details of structures, you have to exaggerate. You have to mention that in your class, that I'm exaggerating that. Otherwise, what happens is people get wrong concepts. Wrong concepts. Science and engineers should not have wrong concepts, wrong proportion. Okay? Why is this important? If the students, all the students, say 5th grader, 6th grader, 7th grader, if they were told that the breathable atmosphere is so thin around the Earth, maybe many people will think it's really serious that we are damaging it. It's a big problem. They will not pollute the air. We live in that thin layer, even thinner than that. Okay. Got it? It's important. There are other reasons too. I read in a physics book, a 10th class physics book, there's a problem given. Suppose a satellite is going around the Earth 40 kilometers above the surface of the Earth. Some speed of that. Satellites do not go around 40 kilometers above the surface of the Earth. It's going to be in the air. It's going to slow down and fall and burn. Okay? 250 kilometers and above. That's where the satellites go, up to maybe 36,000 or something. Okay? So please do not talk about arbitrary numbers. Do not make up these numbers. Look up a reference. It's that simple. Okay? So that physics book should be thrown out, or could be kept as an example of somebody who didn't know what he was talking about. Unfortunately, that physics book was written by or reviewed by 10 PhDs, professors, doctor, this, that, right? Wrong. There were hundreds of mistakes like that. You cannot do that. That's unfair to the students. All right. So let's go over a few similar things. What percentage of water on the Earth is sweet water? It's very important. Air, water, these things are extremely important. Only about 2 to 2.5%. The rest is saline or saline water, salt water. You cannot drink that. So let's preserve the earth. Let's take care of the air and water. It's this thin, only 2% of water, sweet water. Okay? It's important. Just learning a lot of things from books is not enough. Okay, let's answer a few more questions. What is the shape of the Earth's orbit around the Sun? Is it, let's say, more like circular, like this, or elliptical, like that? What is it? Calculate that. Calculate. You'll be surprised. It's an ellipse. Yes, it's elliptical, but very close to a circle. Very close to a circle. Only a few percent difference. Okay? All right. So you can ask many things. You cannot probably read it. What is the speed of the surface of the Earth? Earth is spinning. Earth is spinning. So each part on the equator has got pretty high speed. And it's about 1,674 kilometers per hour, roughly. Okay. The speed of sound is only 1,235 kilometers an hour. So this is moving faster than the speed of sound. So why don't we hear the sonic boom? Ask these questions. First to yourself, find the answer. If you don't know the answer, if you cannot think of it, look it up, think about it, then ask the students, why isn't there a sonic boom? If this Earth is rotating that fast, faster than sound, and there is air in contact, why isn't there a sonic boom? I'll give you a hint. Think about relative speed. Okay, air is turning almost at the same speed because it's so thin. It's turning almost at the same speed as the Earth. Okay, collect such simple, brain-teasing questions on every topic that you teach, whatever you do. Just do not just write down what's written in the book. Okay. Firstly, some of them may be wrong. Secondly, you're not helping the students. A few things you have to take from the book, but also once in a while throw in these kind of brain-teasing questions. Let them think about it. Okay? All right. In science and engineering, the concept, all these things are important. The concept is important. The sense of proportion is important. Size, we should know. We should not just write down, let's say it's A. How much is the value, roughly? If you're talking about a real thing, it should have real value. Okay? The numbers are very important. It's not always ABC. Numbers sometimes may not be possible yet if you're doing purely mathematical work, but you should probably tell them, let's say A is 5. What? 5 meters? What? Plus minus sign. Some people say, oh, I just missed the plus minus sign or wrong sign. It's really important. Really important. Okay? Units are very important. Sometimes people mess up the units and satellites fall down. Okay? Big crashes can happen. Units are very important. Follow consistent unit. Do not say, oh, I just made a mistake there. No. Okay, relation with other quantities. Whenever you are talking about something, how does it depend on the other quantities? Those things are very important, which is basically related by formulas. Most of the time you can have a formula. Sometimes you don't have a formula. You may have empirical formula. Okay. When you do a calculation, the result of the calculation is very important. Formulas are important. Calculation results is important. You cannot say I made numerical error. No. Verification after you get the results, after you get an answer, solve a problem, verify the results. All these things are equally important. Concept is probably more important than the other things. If the concept is wrong, all these things make no sense. But all of them are important. Okay. Science and engineering is not easy. Okay, good. So what did you learn from here? You must be correct and precise about what you are doing, what you are showing, what you are teaching. Do not mislead. No misleading nonsense like Earth looks like this. No, it doesn't. Earth looks like this. Atmosphere looks like this. No, it looks like this. It's that thin. Details you have to exaggerate. So remember this. Please take a note of this. You have to practice that. Let's go over something. If you want, you can take a minute break, pause, and then come back. I will continue. Okay, here's a sample class lecture. Let me choose a topic, physics, because that's my favorite subject. That's one of the most fundamental subject of science. It can explain almost everything if you understand it. All right, introduction. This is the kind of lecture I give to the students. Okay, this is a sample class lecture. Today we are going to learn about motion of bodies. Okay, motion of bodies. You could define what bodies are now, what motion is, but I'll skip that. We'll do it at a later point. We are going to learn about motion of bodies. So, the teacher has to be very active. They have to ask questions every now and then. Let the students think and come up with answers. So, the teacher says, if I put a body, say a book or a piece of wood or a toy car on a table, like this, here I've taken a solid body, okay, on a table, what does it do? Let them think. Let them answer. Ask them, what is it going to do? Somebody say, nothing. That's fine. That's the correct answer. Somebody say, well, it just stays there. Yes, correct answer. Try to agree with them. If they are completely wrong, slowly lead them into thinking right. So basically, it just stays there, which is true. That's science. Observe, think, and come up with an answer. Good. Students say nothing. It just stays there. Yes. Teacher says right. So let's write that in a fancy way, because engineers and scientists have to use very good sentences using technical terms. So instead of saying nothing, it just stays there, write something very nicely. We are going to be scientists. Right? If a body is at rest means not moving, it stays at rest. And that's a very good observation. This is how scientists think. Okay? Good. If a body, write that on the whiteboard or blackboard. If a body is at rest, it stays at rest. Now, if I want to move the body, what do I have to do? Ask the students. Somebody, so you can hit it. All right, that's fine. You can push it, pull it, okay? Blow on it very hard. Something. So yes, we'll write that down. The students say that. You say yes, right. So we can write. You have to write this part here. Modify writing. If a body is at rest, stays at rest, unless an external force is applied on it. When I push or pull, I'm putting an outside force, external force on it. Then it may start moving. Okay, good. The teacher said that means a body has inertia. That means it's lazy. Body has inertia. It's maybe a new term for them. Inertia. Just don't say body has inertia. What is it? That means it wants to stay the way it is. It doesn't want to move if it is at rest. Okay? So it's called inertia of rest. If it's at rest, it wants to stay at rest, doesn't want to change. We need to apply an external force to make it move. Okay? Now, just to entertain them, you do a simple experiment. Like I have a glass here. I hope you can see a glass. I put a cardboard or something, and I put a coin. Let's say that's a body. That's a body. I put it over there. Okay? And then I suddenly move this, hit this cardboard. Okay? Do it carefully. Do it a couple of times. You'll get used to doing this experiment. I hope you can see. The coin fell in here. Coin wants to stay where it is. Coin did not fly with that cardboard. Okay, do that again. Let them do it. Let them do that experiment. Okay? And they'll say, okay, the body at rest wants to stay at rest. Good. There are some experiments similar to that in some books that are completely wrong. They use a bottle and a pen cap and a roll cap. It doesn't work. They have written this experiment in in the books have not tried it themselves. They are bad teachers. They should be punished, sent back to my school. Okay, do this coin, postcard, glass experiment to demo inertia. So what does inertia mean? Something is at rest. It doesn't want to change. It doesn't want to move. So it's got a property that's called inertia. Okay, inertia, not inertia, not shia, inertia. Okay, now comes, what is a body? I've been talking about a body. Body is anything made of matter. I hope you have taught about matter earlier. Okay, matter, like a ball is a body, a table. Okay, this is a body, that's a body. A drop of water, that's a body. Water is also a body. It's just this fluid matter. Okay, you are a body. A car in physics, a body, object, all these things mean something very similar. A body, object. A car is a body. An airplane is a body. A planet, entire Earth is a body. Okay, depending on the problem you're solving, you can say that's a body. Anything that has mass, matter has mass, right? Anything that has a mass is called body in physics. So they learn body, they learn force, they learn rest, they learn inertia, and all these concepts you explain very simply to them. Now you have to ask them questions. Why are we saying external force can move a body? And tell them to think about it. External means outside, applied from outside. So they have to think. What about internal force? They have to think about it. Maybe inside the body there are some forces acting. Okay, little parts are pushing little parts, are pulling little parts. What about that? Okay, let them think about it. You can answer them later, maybe in the next class or after a break. Question, what is motion? We have been talking about, let's learn about motion of bodies. You know, bodies are things. Motion of body. What is it? Movement. Change of position with time. How with time it's changing its position. Now it's here, now it's there, so there's some motion. Okay? Anything that's moving, we say it's got motion. All right, good. So what did we teach them? These are very small letters. Probably you cannot read. I'll make it larger and make it easier for you, or I can supply you the PowerPoint presentation file. You can print it out for yourself. Now suppose a body is moving. Okay, a body is moving. I push the body and body is in motion. It's moving. What happens to that body? Do that experiment in the class. Don't just draw pictures. Many children cannot imagine things from the picture. The first few classes, show them the real things. Slowly they will start imagining. Okay? All right. To develop that, you have to show with real body. Take a piece of wood or a book, put it on the table and push it, and it starts moving. Okay, good. Then move your finger away. Says it was moving. What happens to it? Students will say, well, after some time it stops, or something similar, it stops. They would think if you push something, as long as you're pushing, it moves. As soon as you stop, it stops. So many people have many ideas, but let them think about it. Okay? Good. Encourage them by saying words like right, good, correct. Maybe you're right. Sort of like, never say, no, you're wrong. I don't know if you have gone through that kind of situation. It feels very bad. Let them think, answer. If they're wrong, slowly lead them into thinking the right way and come up with the answer. Okay? If a body is moving, it stops after some time. You write it down. Okay? That is what most people would say. Do that again, that experiment. So that's what we see, that's what we'll write down. Okay? But a scientist would think deeper and ask, what if kind of question. Why did it stop? What if the body was not on the table, it wasn't touching the table, but it was in water? or air. It was just moving in air with the same speed. I hope in kinematics you have taught them about speed and velocity and things like that. Okay, so you can give a demo, take the same body, throw it in air. Students, it will fall. You say, okay, yeah, that's correct too. Will it go farther or will it stop just the way it stopped on the table? Some people say, oh, it will go farther. They can imagine that. Have you ever kicked a ball on the grass? If you kick the same way but in the air, which one goes farther? Ask them. They say, okay, on the grass there's something happening. The ball stops very quickly. In the air, less. Then you tell them. Now imagine if I threw it in vacuum. Vacuum, all the air has been sucked out, like in space. Vacuum. Will it go farther? Some say, yeah, farther. Then you encourage them. You ask them, will it stop? No. Here, on the table, is something called friction that was trying to stop it. You introduce that word. Don't define yet, but they'll get. Water was trying to stop it. Air was trying to stop it. A little bit. Space, there's nothing to stop it. So it will not stop. It will be difficult for them to understand it. It's not that easy. We write down, it continues to move, and we think they understood. They don't understand. Students say, well, it will go even farther. Some student may be very bright. They can probably imagine just the way a scientist is. Really, nothing is stopping it. Why would it stop then? It will keep going. Yes, that's it. Very good. So what we wrote was not right. That we wrote here, if a body is moving, it stops after some time. That's not correct. Do you see what I'm doing? Sometimes what we see, at first sight, what we say is not really correct. We have to imagine, we have to consider what if. That's how you create scientists, okay? So you write down, you correct that one, strike that one, wipe that out, or with a mark, cut that out, and say, if a body is moving, it continues to move. See, this is how the scientists make progress in understanding. Whatever they see, they carefully observe it. Just seeing is not enough. Observe what's happening. Let's see very carefully. Think about it. Then imagine what if, why not, those sort of questions, and try to understand. Okay? This is how you become scientists. Now, if the body is moving at a constant speed in a straight line, take a steel ball and just roll it. Okay, fine. Come prepared to the class. Don't just look for chalks and a duster. Come prepared. You have to spend 40, 50 hours to prepare a 1-hour lecture. Okay? It's not easy. Science and engineering teachers, they are creating futures. They are creating little gods. They will create things. Okay? So you have to take it very seriously. Your job is very important. Okay, so take a little marble or something on the table, roll it on the floor. If it's moving at a constant speed in a straight line, what happens if I apply a force? You can use this one or the marble. Most people think you're applying force in the same direction, and they would probably say it will get faster. That's if they understood something. See how you're leading them to understanding the concept. It goes faster. Some students may say it depends on which direction you apply the force. Those are the very smart ones. They'll definitely become great teachers, scientists. Yes, if I apply a force in the same direction as its motion, it'll go faster. You're right. But what if I apply a force in the opposite direction? That is opposite to the motion. Students will get it. They'll say it will stop. It'll slow down and stop. Right. Now, if it's moving in a straight line at a constant speed, and if I apply a force sideways, show it to them by experiment. Don't just talk, okay? Take something, move it on the thing and try to apply the force sideways, forward in the direction of motion, backwards. Do it. Let them do it too. if they are interested. Okay, apply a force sideways. What happens? It will go sideways, it will turn, it will, all kinds of answers you may get. Let them participate, let them stay awake instead of getting bored and fall asleep. Oh, yes, it will start to turn or change direction and not go in the original straight path. Originally it was going straight. Use a marble. So we can write a body moving at a constant speed in a straight line will continue to do so unless an external force is applied. If you apply external force, it cannot move at a constant speed in a straight line. Depending on which direction you're applying the force, this motion is going to change, right? All the things you have already explained, let them think about it again. So this is also a kind of inertia. A body continues to move in a straight line at a constant speed unless something external tries to change it. So it wants to stay in constant speed in a straight line path. That's also some kind of inertia. That's called inertia motion. Inertia motion. It wants to stay in the same path at a constant speed if it's already moving. Okay, wants to stay, doesn't like change. External force can change it. It is called inertia motion. Many people, they teach all kinds of things. After several years, they say, but I haven't understood what inertia is. I know all kinds of theories and laws, but what is inertia? Let them think at this time. Okay, good. Let me see if I have any other material here. Yeah, Sir Isaac Newton. His picture in his book. Okay, have you ever seen what his book looks like? Have you ever seen what he looks like? No. Okay, you can tell something about this great scientist, probably father of modern science. Okay, one of the fathers. All right, these two sentences that we wrote down, if you combine them together, write that down, okay, are the most famous, one of the most famous laws, and it's called Newton's first law of motion. You just created a law just by thinking, I'm sure, doing some experiment that Newton, a great scientist, took years to come up with. For thousands of years, nobody came up with this, and these students just did it in front of you. Okay, so encourage them. Encourage them. Okay. First law of motion, also called law of inertia. There are two more laws of motion, which you'll learn later. Okay, Newton's laws of motion. There are three of them. You just created one, reinvented it. Okay, Newton created a long time ago. Okay, not created. Actually, all these are discoveries. These are natural laws. We are trying to find out about these laws. Nature already has many laws. We are trying to get close to understanding how nature works. Okay, Newton's first law of motion, also called law of inertia, is a combination of those two sentences. A body at rest, very slowly. You have to understand every word. A body at rest stays at rest, and a body in motion continues to move with a uniform speed, it's constant speed, in a straight line, unless a net external force acts upon it. So that's the first law of motion as written by Newton. So it's called Newton's first law of motion. This means if a body has any change of motion, rest to motion, motion to rest, or motion is changing, speed or direction is changing, that's called acceleration, which you have learned earlier, probably in the kinematics part. Change of motion, change of speed, change of direction, all these things are acceleration. Change of velocity is acceleration, rate of change of velocity. There must be a net external force acting on it. Okay. If a body has any change of motion, there must be a net external force acting on it. Conversely, that is opposite, you're teaching some English words too, fancy English words. Okay, it's opposite. Conversely, if there is a net external force acting on a body, its motion would change. That is, it would have an acceleration. Did you understand? Acceleration. Yeah, it's pronounced as acceleration. Okay? Acceleration is probably not wrong either. But acceleration, that part has to be louder. Okay. Cause and effect. Force is causing the motion to change. The effect is the motion, change of motion. In science, quite often, we talk about cause and effect. Something is causing and some effect is happening. Okay? That's the kind of relation we look for in science. Okay, so force can cause change in motion. If there is a change in motion, there must be a cause, force, external force. Acceleration means rate of change in velocity, change in speed or direction or both, depending on which direction you're applying the force. Okay? Give some pauses. I'm going over very quickly because you already know these things. You have to spend years to understand most of it. I don't know if you understand all of it. I don't understand everything about it, to be honest, about physics. Top physicists say they probably understand 4%, 5%. That's how this nature universe works. Top people. But they are so humble, they say, I understand nothing. People who understand a little bit, quite often they think they understand everything. And that's not correct. That's not good. All right, the words can differ from book to book. This laws of motion that you saw, first law of motion, it can be written differently. Newton wrote it very differently. But later, we added few things, modified it. The net external force was added later. Okay? Words can differ from book to book, but the meaning stays the same. Think and memorize this law, at least one form that looks good. You choose the best form, give it to them, and say, okay, understand, memorize it sometimes. Otherwise, sometimes they have to say this in job interview or in exams, and they'll be confused if they know too many versions of it. One correct version they should memorize, but they should know that there are other versions too. Meaning is more important. Okay, think why we wrote net external force. Let them think. I said, what is net? Net is total. Net here means total. English is a difficult language. Net has so many meanings. Mosquito net, fishing net, okay? Here, net means total. Suppose there's a body. If I push it here and push there too, equal and opposite, will it move? No. So total is zero. That's why it's not moving. There has to be some total force, okay? I can push here a little bit, but push harder on this side, then there's a total force, then it will move. That's kind of external force, net external force. Think, what is the use of this law? Okay, we thought about motion of a body and created some fancy looking law, came up with by observing, wrote it down, and what's the use of this law? Ask them, do you think this law is really true? We just made up something from our observation and imagination, what can happen in a vacuum. Is it really true? Have you ever seen anything that keeps moving in a straight line? Trains, they move in a straight line, they'll stop. Everything stops. And why in the law, a scientist, you put that it should continue to move unless there's an external force? Let them think about these things. It takes a long time to imagine, absorb, think about things. Only then they can apply it, okay? Ask them these questions. It's opposite to our daily experience. That's why Newton was genius. Anybody could have written anything that moves, it can stop. Okay, I'll not repeat anymore. You're all smart. You have probably figured out what I'm trying to get at. So you have to think beyond what you see. Okay, roll a steel ball, changes direction with a magnet. It's going to be a lot of fun for the students. Okay, a lot of fun. They don't know much about magnet, but they know something. Magnets attract iron. Okay, before you do these experiments, try it before you go. Many experiments go wrong in the class and the students lose respect for you. You learn two more laws of motion. Newton's laws of motion have three laws. Two more laws in the next lesson. I'll give you a hint, but the next law is going to be. Until now, we are talking about if you apply a force, motion changes. But how much force you apply to change how much motion, those things are called quantitative things. Quantitative, how much? Physicists don't just stop and say, if you do this, this happens. How much? They need to know that too. Okay? So we'll talk about that one. So, Sir Isaac Newton, you have to tell something about him too. It's written in the book, make up a story from his life, something that's very important related to physics and so on, not private life. I don't like that. Okay? Just talk about. Was a great scientist. You can tell he was from the United Kingdom. I don't know if that time it was called Great Britain or just England, whatever. Nearly 300, 400 years ago. You can throw in which year he was born, etc. Okay. You can tell that he was a very weak child and he grew up with his grandmother. It's okay. He suffered a lot. But he forced himself to become the greatest scientist by thinking, doing experiments, writing laws, working very hard. Okay, he spent many years discovering many laws. Not only these laws of motion, there are hundreds of laws he's come up with. Okay, of nature, and wrote them in a book called. This is the book. About 300 some years old book. Okay, and that's Newton's picture. Sir Isaac Newton. Not Newton, 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 Sir Isaac Newton. Okay. The book's name is Philosophiae Naturalis Principia Mathematica. They'll be so surprised. So memorize this name. You can impress a lot of people. Philosophy. This is written in Latin. In those days, people wrote scientific things in Latin language. Okay. Now, most people write in English, German. For those days, most of the books in science used to be written in Latin in Europe. Philosophiae Naturalis Principia Mathematica. In English, it's called Mathematical Principles of Natural Philosophy. Your understanding about nature. All this is natural philosophy. Okay? We use some mathematics. If we have not, we will use some mathematics later. All these things that he studied, he had put in a book, memorized the name of the book. This book is also simply called Principia. That's Newton's Principia. Okay, but full name is Philosophiae Naturalis Principia Mathematica. They learned a lot from you. The students learned a lot. They look up to you like heroes. He knows so much, or she knows so much. They'll try to imitate you. Be excited about teaching. Show them these examples. Ask them questions. Ask them to solve simple problems. Let their imagination connect with their reality and see beyond. You'll make hundreds and hundreds of scientists. Thank you.